Hi everyone, and welcome to the talk From Crypto Paper to Cryptocurrency, the Cardano Consensus Layer. This is an extended version of the talk that we present at the Real World Crypto Symposium 2021. My name is Christian, and this is a joint talk with Philip and Duncan, and we were supported by Peter Gashi, Agelos Kias, and Alexander Russell. The talk is roughly structured into 4 sections. First, I will cover some general aspects from theory to practice. Then we discuss the formal methods and implementation correctness aspects that are related to the Cardano consensus layer. Then we discuss what could have gone wrong if we hadn't followed such a strict and methodological approach to the implementation. And finally, we discuss some aspects on our path to decentralization. At its core, the Cardano consensus layer is a distributed computation over a network. It's a cryptographic protocol, and as such, we fix in our papers a formal model for protocol execution. We model the parties that run the protocol by interactive machines. We formalize the assumed resources that are available to the protocol. For example, we formalize which type of network we assume. Is there a clock? Is there a random oracle? With formalization, I mean to specify such assumed real-life objects in a more abstract manner that is more friendly for mathematical proofs. We could, for example, imagine writing the specification of a network as a pseudocode or any other language that helps us to do the proofs. Here we already see a strong interplay between theory and engineering. An abstraction must capture all relevant properties but should not omit details that we later deem relevant. This is a very subtle task. Part of our execution model is also an attacker. So we must assume that not all parties, they run in favor of the protocol. There might be a central adversary that corrupts certain machines, which might then interfere with the protocol execution in an arbitrary way. So our protocols have to be resilient against such attacks. We must also keep in mind that parties might be rational. So we must incentivize honest behavior. We must incentivize the people participate for the good of the protocol. Finally, we also have to deal with machine failures, which means that parties might disconnect for a certain amount of time from the network and later reconnect, and they must be able to bootstrap the current state automatically. So other parties might help to synchronize, but this should be part of the model and the protocol must support this. Overall, this gives us a very fine-grained security model, coupled with a very strong notion of security, namely composition, where each external input, such as a transaction, might depend on the entire view of this and other protocols. We get actually a very meaningful security statement if we prove security properties in such a manner. Why? Because our model of security assumes a lot of very bad actors and is in this sense worst case. And if we are confident that our model is like worse than the real life will be, then actually our security proofs is meaningful to practice. If we believe we have captured all relevant properties, an adversary is more powerful than in reality it would be, then our security proofs really mean something. On paper, we know what the Cardano consensus layer should implement. It should realize a ledger that is persistent and alive. Persistent means that it records transactions and smart contract state transitions that are immutable. It should be live because we want that transactions get added over time to this ledger. We also know that Ouroboros is a Nakamoto-style proof-of-stake blockchain protocol that realizes such a ledger. To recall, a Nakamoto-style blockchain kicks off with a genesis block. Then in each round, we have a lottery who the next block proposer should be, and proposers are elected proportional to the stake they own. This gives rise to a fork structure or a tree structure, and although we might not agree on the most recent few blocks, we always know, or we prove, that we have always a large common prefix. We have chain growth, so the chain grows. We have chain quality. We have enough well-formed blocks. And this is all proven under an honest majority assumption, meaning that the stake is assumed, the majority of stake is assumed to be in the hands of honest parties. Ouroboros has developed over a series of works to achieve the resilient design it has today. Each of the papers you see on the left had to overcome specific design challenges, as we have seen before. All these papers, they live in an abstract, proof-oriented world. As such, they have abstractions of components, they're written in pseudocode, we make asymptotic statements, hence there is still a quite large gap to bridge between a theory and an implementation. From a conceptual point of view, also the sequence of steps make a lot of sense. First, the classic version of Ouroboros that appeared at Crypto 2017, it assumed a synchronous model of computation and static corruption. In Prowse, the rigid message passing round structure was removed and adaptive corruptions were tolerated. A reward sharing scheme for stake pools was added to establish an equilibrium with a large number of pools with high commitment to the system. In Genesis, we dealt with fluctuating participation and made it possible that joining after disconnection is possible in a decentralized manner. Later, we improved the resilience by less dependency on an external timing service. And finally, we get more functionality by privacy thanks to the design of Crypsinus. This looks all so ordered, but is that really the case when we move from theory to practice? With this question, I would like to pass it on to Philip. Thank you.
Excellent question, Christian. Thank you. The answer is, of course, that things are messy in production than they are in a research paper. After we had the original Ouroboros version as a preprint, we started an engineering effort to build a cryptocurrency built upon that protocol. We launched that in September 2017, and having something running in production, we then realized basically what was still missing. We realized pretty early on that we couldn't launch that system in a decentralized manner yet because we didn't have the reward schemes and the delegation mechanism that we needed in order to have it running efficiently. And we also realized that certain aspects of the consensus protocol needed refinement, which then spawned the upcoming research papers. It was a continuous process of getting an improved understanding of the requirements on the system. We also realized that the engineering that we had done for the first version was very perfect, which is basically never the case. One of the big things that we had in the first version was that the whole thing was too tangled, so there was no clear separation between the different modules, and that made it very hard to switch from one version of the consensus protocol to another, or to do changes to the ledger rules. And so we started a re-engineering effort to get a version of the system that was much more modular, where you could make changes to the consensus protocol or to the ledger independently from one another and make a transition and accommodate basically all these improvements that the researchers did to the consensus protocol. So in 2019, that was ready for production, and we started that alongside the old code, and then afterwards we were able to retire the old code base. And then in summer 2020, finally, we were able to decentralize the system because all the components that we needed were ready. And the things that are still to do is like adding the Genesis, Chronos, and the upcoming versions of the consensus protocol, as well as adding new features like smart contracts to the system. Now, the next thing that we want to cover in the presentation are how we made sure that all the nice guarantees that we have from the research papers, the proofs that we have on the theory side, actually carry over to the implementation, so that we have something that we are confident is correct, and that we can also show evidence that it is correct. And when you want to do something like that, there are some questions that you have to ask yourself before you start. Like, what's the required level of confidence that you want to have in your system? That is correct. What time do you have available to implement it? What about the requirements? Are they fixed? Do they change during the course of implementing the thing? And what's the difficulty of the whole thing anyway? And depending on how you answer those questions, you can pick different approaches. If you don't need much confidence in correctness and you can issue fixes if something goes wrong and you want to be very quick, then you can do this agile move fast and break things approach, but that's not good for a system where like having an error in production compromises it and leads to a loss of money. On the other hand, you have the full formal approach where you basically specify everything beforehand and then prove that everything is right. And then once you have done all the proofs, you start implementation, which tends to be slower, but you have a great degree of confidence in the correctness. You can also like choose a middle way and use some methods, which we will show you some in the following sections, that do give you great confidence in the correctness, but that are quicker, and I would argue even quicker than the startup way, because you make fewer mistakes, and those mistakes always cost you a lot of time. So the question is not really, do I want to implement things correctly or do I want to implement them correctly? But you should really aim for both, because doing them correctly saves you time, because you don't have to fix bugs that are already in production. There's a variety of tools that you can use, from formal specifications and proofs about properties of those that you can either write by hand or even using a theorem prover that can then check actually that you don't make mistakes in your proofs. You can apply model checking sometimes. And another tool that we use greatly are property-based tests, where you write down properties that you could prove, but you use the actual code and generate randomly test data that then checks whether those properties are satisfied for arbitrary inputs, basically. And the nice thing about that is that it's often quicker than doing proofs. And it also is based on the actual implementation and not just on a specification. And since there can be a gap between the specification and the implementation, checking those properties on the code itself is great. And which one of those properties, which one of those tools you can apply depends on the properties of the system that you are implementing. For instance, do you have determinism? Do you have concurrency? What about the state space? Is it finite? Then it's great for model checking. Otherwise, it might not be so great. And so you have to look at basically every component that you want to build and answer those questions about what is the methodology that I want to use. So looking at Cardano in particular as a cryptocurrency, the thing looks really quite messy on first sight, because you have this tree structure of blocks, and then you can revert blocks when you jump to a different fork. So you only have eventual consistency, and also it's a distributed system, so different nodes might not even be in agreement about what the current state of the system is. And that is quite hard to formulate. On the other hand, if you look at just the contents of the thing, at the transaction ledger, then for any given history, that is just a linear view of one transaction after the other. And so one of the crucial design decisions that we made was to cleanly separate those two. So we have modules that handle the concurrency, that handle like the consensus part and the networking part. And that is like the messy world of concurrency and distributed computing. And then we have the actual transaction ledger, which only ever is presented by the consensus layer, one linear view of transactions. So you can look at the consensus layer as like picking one chain and then presenting that one chain to the transaction ledger. And so you never have, when you are applying transaction, you never have to think about how do I roll them back? What do I do there? But you have that cleanly separated. And that's something that wasn't there in the initial implementation. And that makes this second version much more easy to work with. Talking about the ledger, we can formulate that very nicely as transition rules that go from an initial state and then do some modification to that state. For example, applying a transaction, which basically tells us to take the state of the system, remove the inputs of that transaction, so some piles of money that are spent by the transaction, and add some new piles of money, some new outputs from that transaction. And then above that bar, we have all the rules that must be satisfied in order for that transaction to be valid in the first place. So the transaction inputs that the transaction users need to exist in the initial state. The transition needs to be balanced overall, and you need to have some fee that has to be larger than the threshold. And formulating it in such a way is possible because we only have one state of the system that progresses through a fixed series of state transitions, and we don't have different threads that might have a different view on that. But it's just a single state that performs some transitions, and it's very nice because it's ambiguous. and concise and precise language to formulate these things. And if once you are clear about those rules, implementing them is not that hard. So below is the actual implementation in Haskell, and if you look at that if you take some time to look at that, you see that it's just a very verbatim translation. So here you have this is a subset of the current UTXO. That's basically that condition here, and so then you have this transition here. It's exactly the same what is below that bar. You have the UTXO. You remove the inputs from the transaction. You add the outputs from the transaction, and that's that. So it's a very nice way of writing a system. Once you have written it in that way, you need to make sure that not only does that implementation, which is just another, we call it an executable specification because it has the same contents as the specification that we have as a LaTeX document to talk about and to reason about, but it's executable and it's the basis for the implementation. But you need to make sure that this executable specification, and with that the implementation itself, that is defined by like the small steps, the microscopic transitions that the system can do, actually fulfills all the macroscopic properties that you want. So that those are things like macroscopic properties are something like the money in the system is conserved when we apply transactions to the system. And the way that you ensure that that is the case is that you formalize those properties, and then you can use the quick check library, which is this property-based testing framework that generates randomized test data and then makes sure that for all that randomized test data, those properties are fulfilled. And you can also go ahead and prove them based on the formalization. And for the ledger, we could do both, which is very nice because the proofs are, of course, exhaustive, and the property-based tests are tied to the implementation itself. When we go to the consensus part, things are a bit messier, so you can't do this very nice and clear style of things. And that is something that Duncan will tell us about now. Thank you very much.
The environment in which consensus operates is messy because it is fundamentally concurrent. And concurrency is hard both in practice and in theory. So when we were thinking about the design of our new consensus implementation, we had to think very carefully about what kind of formalisms or semi-formal techniques we ought to use to give us that balance between correctness, which is really what ensures security, and speed of development. So while it is absolutely possible to take a fully formal approach to concurrency, fully mathematically formal approach, it is just harder than a more mathematically tractable problem like the ledger. So the approach we decided to take was advanced testing techniques, including property-based testing with deterministic concurrency simulation, and also making use of advanced type system features to enforce invariance. And then as a completely separate parallel project, we decided to investigate the completely formal approach and try to make use of results later on. The approach we took to testing the consensus implementation was to write it in such a way that we could run the exact same code both in production for real and also in a deterministic concurrency simulator. And that means that we can write properties about the concurrent code which observe the trace of the execution of the code and observe interesting events, and they can write properties that determine that can say whether or not that is a reasonable or an unreasonable execution of the program. And the way we do that is a simple mocking technique where we capture all of the concurrency primitives. So application codes are using concurrency primitives such as read queue, as in this example here. It's captured in an interface, and there's two implementations of it. One, the real production version, and a version that runs within the simulation. And this means that we can use these property-based testing techniques, writing properties about concurrent code that looks at the trace of execution. And because it's deterministic, we get the brilliant property that these things are reproducible, and we can shrink to minimal counterexamples, which is a fantastic technique for really understanding a complicated failure, reducing it down to its smallest possible example, and that very often shows up what the problem is straight away. One of the other lightweight formal methods that we've used is to design our application level network protocols as very simple state machines with the property that in each state there is exactly one sender and one receiver, so only one peer has agency at once. And this means that we can guarantee freedom from deadlock and freedom from race conditions. And we're able to enforce this property, make sure that we don't make mistakes with this property, by enforcing this using the Haskell type system, which means that violations are prevented at compile time. So here's an example of one of the real protocols. And as you see, it fits on one slide. It's really very simple. And we have a number of simple protocols, and we multiplex all of them over a single TCP connection. Now, I mentioned that we've taken two approaches in parallel. In parallel to the existing development effort, we've done an R&D parallel project to investigate a completely formal approach to the consensus concurrency difficulties. And I want to mention briefly about that project. We hope to incorporate the fruits of that project later. The goal is to establish some kind of equivalence between the high and low-level designs. So the high-level design is exactly as in the paper, exactly figure 2 in the paper. And the low-level design is a design that corresponds to the real design that we have come up with, and it has to be a practical design. It has to work in the way that real networks really work, and crucially, it has to operate in bounded resources. Now, we don't want to try to establish an equivalence between two very different things, because that's very difficult. A low-level design and a high-level design in a monolithic way. That kind of proof is very hard. So instead, we take a modular approach to the design and a modular approach to the proof, and these two correspond to each other. So the idea is that we do a series of design refinements to get us from the high-level design to the low-level design. And then the proof is structured in exactly the same way as a series of equivalence proofs of an appropriate notion of equivalence. And the intention is that these should be fully machine-checked formal proofs. So the results that we have so far is that we have developed an asynchronous version of a process calculus, heavily inspired by the classic pi calculus. We've done that using the Isbell theorem prover. We've proved all the usual properties that you would want about a process calculus, and we've made a nice framework within this process calculus, within Isabelle, for establishing bisimilarity results, which is the main kind of equivalence that we are interested in. Or at least they're typically based on bisimilarity. And in addition to that, and that is honestly the substantial chunk of the work, is simply developing the process calculus, we've also formalized initial versions of the Ouroboros BFT and Preos, as described in the papers. So those are those high-level versions. And we've done a proof about one of the first design refinements, which is showing the equivalence of message broadcast, which is what is used in the Ouroboros algorithm descriptions, equivalence with relaying over a network. And we've also proved another result about bulk versus incremental chain selection. So in this example, we wanted to prove the correctness of this design refinement, the refinement that goes from message broadcast to message relay over a directed graph. So on the left-hand side, we have 4 nodes communicating via a central broadcast channel in this example, and this is asynchronous with loss and duplication. On the right-hand side, we have 4 nodes connected via a graph, which is connected but not fully connected. And we've been able to prove that these two are bisimilar. Now, these have this nice graphical notation here, but they correspond to precise statements, precise descriptions within the process calculus. Now, it's actually equivalence with a little interesting wrinkle, and in fact, doing the proof, showed up that wrinkle. And this is the kind of reason why we want to do these kinds of proofs, to see if there are additional things that slip by when you first think about it. So intuition and proof are not the same thing. So in this example, it turns out that if you relay a message from A to B to C, and it arrives at C, so it happened the case that there was no loss in that case, then we actually know, we can infer that it did in fact arrive at B, whereas you cannot infer that in the case of perfect message broadcast. In that case, all the failures are independent. So we're able to insert additional loss into the relay case, and then we can show that they are bisimilar. So let's take a step back and look at how are we connecting our papers with the code that's running on the real system. How do we connect our intention with the real code that is running? So it's worth noting that we've taken a selective and sparing approach to where we apply formal and semi-formal methods. And that's really been focused in the ledger rules and the consensus, where there's really greatest scope for expensive mistakes. So starting with the ledger rules, as Philip was describing earlier, we started with the papers, for example, the reward scheme, other internal technical reports, and other business requirements about what a cryptocurrency ledger ought to be like. And that informed our design of the formal ledger rules, as Philip explained earlier. The PDF set theory, nicely explained, presented a description of those rules. And then we established the connection between those rules and the executable version, which is really the thing that's really running on the system, by careful audit and by checking the properties, using those properties as tests on the executable version of those ledger rules. So that establishes a very strong connection between what we have intended in the formal ledger rules and what is actually running. And so the formal ledger rules are the canonical description of what the system does, informed by the papers. But obviously there's not a completely formal connection between the papers and the ledger rules. The ledger rules, as described, are the formal description of the system. Then on the other side, with the consensus, obviously our starting point there is the Ouroboros papers, and those inform both the design of our consensus implementation and, crucially, they tell us what properties to test and what environment do we test them in. And by environment I mean failures, adversarial behavior, etc. In particular, we can construct environments that are so extreme that consensus is impossible. And we need to be able to test and know whether or not consensus should be achieved, so that we can check the property that in fact is. And that's exactly what we do. We take our real implementation, which we can run in reality and in simulation, as I described earlier, and we apply this systematic randomized property testing approach. And one of the main properties is, do we achieve consensus when we expect to, and which we know from the environment that we can construct. Where we insert delays, where we insert failures, etc. And so that tells us, if we ran it in an environment where consensus was expected, did we actually achieve consensus? And that's the main property that gives us assurance that our consensus implementation does what we think it does. So that's the big picture. We have quite strong, but not completely formal, but yet really quite good evidence, quite strong evidence that connects our intention through to the real running code in the system.
In the remainder of this talk, I want to present to you things that could go wrong in such an endeavor, and that includes things that you need to be aware of when actually doing the design, things like certain edge cases that we found with property-based tests, and also operational concerns when dealing with a decentralized system. So first, let me show you an example of quite a subtle bug that we found with property-based tests. In order to understand that example, you need to know that in order to operate in a decentralized manner, in an open network where everybody can post things and send you data, but where you have limited resources, we need to do aggressive filtering of the incoming data in order not to be overwhelmed in a denial of service attack. And so one of the things that we do in Cardano is that we try to select the chain based only on block headers before downloading any actual block data. And we can do that because each block header contains a signature, and we can check that signature and can check whether the owner of that key is actually eligible to produce a block based on the stake that they have, and that stake is static for some period of time, for an epoch. And so we have that forecast range. If we know the ledger state at some point, then we can say for any block within that range, we know the stake distribution, and so we can check the headers. Now, what can happen if we are in a bad situation where block production for some reason or another holds for a longer time, that we get a block outside of that forecast range. Now in this case here, where that block directly attaches to the block that we currently have, that's not a problem because we know that there's no block in between that could change the stake distribution, and so we can just use the current stake distribution. But in a more complicated setting where we have a block that's not connecting to our current tip but it forks off earlier, we might have to download an earlier block in that fork in order to know the stake distribution that determines who has the rights to produce that block in order to check the header. So in that situation, we would need to download another block in order to change whether a potential chain is valid or not, and whether we want to switch to that. So the proposal that we had for this is to only do that, only download actual block data before deciding on which chain to follow, if there was no other way to continue following any of the chain alternatives that we are presented by our peers. And that's what we implemented. But then we saw that our property-based tests showed us that we had disagreement between the nodes on what the actual best chain was. And the thing to notice here is that we didn't write a unit test for specifically to see whether that worked, but we had just general tests that produced different chains and sent them across the network, and then saw whether the nodes would converge on one view of the truth or not. And then those tests failed, and they didn't just fail, they also gave us a minimal counterexample, which looks like this. So in that case, we have two possible chains, and both of them would require us to download a block in order to validate the last block in that chain. The thing is, if we implement that rule that we say we only download blocks if we can't follow any of the chains that we're presented with other than that, what happens is that some of the nodes would download that green block, and then at that point they are able to follow the upper chain. And so the condition that you need to download block data in order to follow any chain is no longer true, and you do not download the blue block, and so you never follow that chain, that lower chain. And other nodes would download the blue block first because they were presented with that chain first, so they would be stuck forever with that chain. And so that's why that doesn't work. And what you see here is that if you were to write a unit test case for that, you would test exactly for that situation. So you would know what's going wrong. And in hindsight, it's pretty obvious what's going wrong, but that's the thing about hindsight, right? And the nice thing about those general property-based tests is that you think about very general properties, like you get agreement. You do not think about this optimization that you are doing. You think about different concerns when writing the code than you are when you're writing the tests, and that makes it that reduces the probability of reproducing the same mistakes in your code that in your tests, and thereby not finding the mistakes. And so that's a real powerful thing about those property-based tests. Another thing, an operational thing that often goes wrong with blockchains is that when you change the rules of the game, you get disagreement on like which rules to follow, and you get a fork. And this has happened with Bitcoin many, many times. So in Cardano, we want to change the rules of the game quite frequently when we introduce new features on the ledger or when we introduce newer versions of Ouroboros. And in order to have that without the risk of forks, we need to have one code base that can understand the whole chain from the beginning to the end, and that evolves over time. And we need to get agreement on when to switch from one set of rules to the next. And that point where we transition from one protocol version to the next can't be hard-coded in the code, because if we did that, then in order to do that, we would need to know when all the operators have updated their software, and we don't need that when we don't know that when we implement the code. And so we have to have some signal on the chain that tells us when we want to do that transition, and we need to have a software that can deal with transitioning from one version of the protocol to the next at a time that's not predetermined when we produce the code. And for that, we've written a software that is called a hard fork combinator, which takes a number of protocols and defines a new protocol as a sequential composition of those protocols. And this hard fork combinator avoids us having a situation where the system hard forks because we have disagreement on which rules to follow between the operators. Another thing that is quite risky is the point at which you decentralize the system. So at first we had a fixed set of nodes that operated the system, and we had control over those. But then we want to open that up, of course, to the community. But that point where you open it up is quite risky for two reasons. One is that the people who are operating the new nodes, they don't have experience with it, so it's not clear whether they will run them in a stable manner. So you can have the system go down because people just have no experience in operating those nodes. The other one is that in order to go active, people have to delegate their stake to one of those operators. And at the moment where you do the switch, most of that stake will not be delegated yet. So you have an increased danger of a 51% attack just because there's so little active stake. In order to mitigate those risks or de-risk it and remove that risk, we introduced a new parameter into the protocol called D, and that determines the fraction of blocks that are still produced by this earlier federation. And then you can gradually shift from D equals to 1 to D equals to 0, where you have full decentralization. And while you are decreasing that D, you can monitor system health, delegated stake, and things like that. And by that you remove that dangerous period. There's other things that can go wrong when you go from the abstract description of the protocol to a more concrete one, which you need if you want to have something running in the real world. And that is that in the papers you have a very abstract view on things like the network, for example, but you need to concretize these things and you need to refine these things when you go towards an implementation. And while you're doing that, you could create new interactions also for the adversary to interact with the system. And you need to be careful not to introduce new interactions that compromise the system and that make it more easy to attack the system. And one example for that is that you have to be very mindful about the resource balance between honest nodes and adversarial nodes. And if you don't get that right, then you create opportunities for asymmetric resource attacks. And that aggressive filtering that I mentioned 3 slides back is an example of that. And there's many more considerations like those, and I hope that gives you an overview, an idea for like how careful you have to be in order to get an implementation that is good and faithful to the papers. Thank you for your attention. We have lots of future work lined up. There are still some remaining gaps between the theory and implementation that we can work on closing. There's also a formalized version of the security guarantees of the Ouroboros paper. There's a PhD thesis about that is about to be completed using the Isabel theorem prover to get formal proofs of the security guarantees. We have to implement the newer versions of Ouroboros and also add new features to the ledger functionality, smart contracts, decentralized software updates where the community itself agrees on like which future software versions to accept or not. So lots remains to be done, and we're working on that happily. Thank you for your attention.